So good evening, is my voice good evening, is my voice audible? Can you please confirm or type in the chat box? you're there in the call, please respond by typing in the chat box or speaking out whether my voice is audible, whether the video is visible, please. Okay. Hello. Am I audible now? Let me check once from the mobile. Oh, yeah. Yeah, so that time I was not speaking, so maybe that time you wrote no. So let's get started. Let me check once. Okay. Mm. Okay. So good evening everyone. I am Shouharda Ghosh, a first year PhD scholar in the Department of Electrical Engineering at IIT Gandhinagar, and I have completed my BTech as well as MTech from IIT Kharagpur in the field of microelectronics and VLSI design from the Electronics and Electrical Communication Engineering Department. And I am the PMRF scholar TA for this NPTEL session on real-time digital signal processing. This is week 8 and we shall be learning about adaptive signal processing and its applications. So this week I'm not solving much problems because most of the problems in the sheet as well as the previous corresponding to this topic are mostly theoretical in nature, which can be easily solved if you look at the lectures as well as the notes. So I'll be mostly looking into derivation as well as the mathematical aspects of the topics involved, because the rest of it is all applications and the nuance technique and the know-hows of the stuff. So in case anybody wants to contact me, this is my email. My voice is not clear. Hello. Let me check once from my mobile phone. Um, okay, so I'm joining from a different device. Okay, so hello, hello, hello. Yeah, okay, fine. Hello, check. Hello, check. Yes, the voice is quite clear enough. I've just checked out, so no need to worry. The voice is actually clear. I think there's some issues with the hardware on your side, so maybe you can check that. Okay, so let's look at what we are going to study today. Hmm. So actually in the previous session somebody had asked a doubt on how we detect a signal frequency using adaptive filter. So I shall do that today first. Before that, let me mention my email ID. It's Shouharda dot Ghosh @ IIT Gandhinagar AC dot in. Okay, and so we shall first talk about detection of a single tone signal that is using adaptive filtering. Okay, so let us mention our basic fundamental scenario. So we have an input analog signal, let's say a cosine signal, a cos omega ct plus phi. Okay, and we also know that cosine of x can be written as e to the power jx plus e to the power minus jx upon 2, sum of two complex sinusoids, complex exponentials. So what can we write over here? A by 2 e to the power j omega ct plus phi plus e to the power minus j omega ct plus phi. So now when we actually observe the signal after a lot of processes, transmission, reception, low pass filtering, RF down conversion. Okay, so assuming that we are operating in a communication system, we undergo a lot of processes, after which we finally receive this signal. The observed signal za of t is finally this analog signal a of t plus nu a of t, which is the noise. But actually what happens is that before converting it into analog, we have this signal in the digital format. So we want to remove the noise in the digital version, because analog in analog there are some disadvantages of noise removal. The analog components themselves add noise, so we want to remove this noise digitally. So what happens in digital domain, where we have sampled period of capital T, so we write that signal as time index of integers, which is za of nt. It is nothing but x of n plus v of n. Okay, and x of n was our, so what did we mention earlier in the previous lecture, that if we want to obtain our sinusoid, the sinusoid that we want to extract, the omega c, the corresponding filter is the narrow band pass filter centered at omega c, where omega c is this analog frequency omega c times the sample rate. Okay, but then in any scenario, if this center or carrier frequency changes to omega c prime, then our normal band pass filter does not work anymore. And why is that so? Because you can very well see that if my sinusoid gets down over here at, let's say, minus omega c prime and omega c prime, where our omega c prime is change frequency, so then this band pass signal will completely cut off this component, and I will no longer get the signal. So you can see we have to have some kind of a mechanism by which we can eliminate, or we can adjust the filter response so that it can tune with the signal frequency. So you need to use a adaptive band pass filter. Okay, So which is our first topic in the adaptive signal processing and its applications. Okay, so let's write down the frame. Let's do a bit of math and then we shall expand on this framework. So consider a signal, discrete time signal Sn, and let's say it's a complex sinusoid a e to the power j omega cn plus phi. Okay, now if I delay this signal by one sample, I get a e to the power j omega c. Just replace this n by n minus 1 omega c plus phi. So now omega c n minus 1 plus phi. Okay, so what do? I take this minus omega out and I can write e to the power minus j omega c a e to the power j omega c n plus phi. Just hold on for a few minutes. Even j omega c. So okay, so what do you see? Here's a constant constant complex term, and what is this? This is our Sn. So we can write S of n minus 1 is e to the power minus j omega c S of n. Now what do? We take Z transform on both sides. Okay, so what happens? S of n has a Z transform of capital S of z, so S of n minus 1 will also have a Z transform Z inverse S of z. Okay, so what do you obtain? Z inverse S of z. From the left hand side and the right side we have e to the power minus j omega c S of z. Now what should I do? Let's multiply the e to the power j omega c on the left side, sorry, S of z. I have S of z. Let's take that to the other side. S of z times 1 minus e to the power j omega c Z inverse equals to 0. Okay, so we note this equation for signal Sn, which is a e to the power j omega cn plus phi. I have a corresponding polynomial, complex polynomial S of z times 1 minus e to the power j omega c Z inverse equals to 0. Okay, this is an equation that we need to keep in mind. So let's see, if I have two signals, one is S1n, generalized, I am generalizing it, a1 e to the power j omega c1 n plus phi 1, and another signal S2n, which is another amplitude, another frequency and another phase. So we can have their corresponding polynomials S1z, the z transform, times 1 minus e to the power minus j omega c1 z inverse equal to 0, and now S2z 1 minus e to the power minus j omega c2 z inverse. Okay, let me check once again. Something's happening. Fine. Okay, so we have these two polynomials. Okay, so now let me form a polynomial, okay, pz And what will be this PZB? It will be the multiplication of this polynomial with this polynomial. These are polynomials in Z. To the power minus j omega C1 Z inverse times 1 minus E2 j omega C2 Z inverse. Okay. So what do you observe over here? This polynomial Pz times S1Z is equal to 0. Why? You see, in this what is S1Z? We know, what do we know about S1Z? S1Z is the multiplication of S1Z when multiplied with this factor of Z inverse gives me 0. So P of Z is multiplication of first factor and second factor. So when I multiply first factor with this, I automatically get 0. Okay. Similarly, when I do this with the second signals transform, so I also get this. So now I add the 2 and what do I get? Pz into S1Z plus S2Z equals to 0. Fine. So now let me generalize this to R signals. Okay. So let me have these R signals as A of I e to the power j omega C I n plus phi I, where I ranges from 1 to R. Okay. So I can write a combination of all these signals as Sn, which where I ranges from 1 to R, Si of n. Okay. So Si of n, so what can I write from this Si of n? I can write it's Si of z times 1 minus e to the power minus j omega Ci C inverse equals to 0, isn't it? That's what I proved just a few minutes ago. Okay. So now what do? We proved earlier that for two signals S1 and S2, when I sum them up, then when I multiply it with the polynomial corresponding to frequency omega 1 and omega 2, then I get 0. So I can extend it to R signals. What do I get? I get P of Z. Okay, what will P of Z be? P of Z will be the product of, okay, so pi, capital Pi means product of the exponential terms 1 minus e to the power j omega Ci Z inverse. Okay. And then what will happen? P of Z times S of Z will be equal to 0. So now what happens to P of Z? What is actually P of Z? P of Z is actually a polynomial in Z inverse, and when I write it is actually a complex polynomial. So when I expand this polynomial, what will I get? I'll get 1 plus a1 Z inverse plus a2 Z inverse, okay, so on till how much? A r z to the power minus r. So what do we get? 1 plus a1 Z inverse plus a2 Z inverse z to the power minus 2 all the way till a r z to the power minus r times s of z equals to 0. Now take the inverse Z transform. What do I get? S of n plus a1 s of n minus 1 plus a2 s of n minus 2 all the way till ar s of n minus r equal to 0. Now what does that mean? S of n is summation over I equal to 1 to r a of I s of n minus I. Okay. So what does this mean? When we have r sinusoids, okay, the nth sample, okay, nth sample can be directly obtained from the linear combination of our past samples of S of n. Okay, so what does it mean? Using the past sample values, I can acquire the present sample value. Okay, this is a sorry this is a predictability property of the complex sinusoids. Now let me extend it to a real cosine signal. So till now whatever I have been talking about, starting from detection of single tone, then this taking the transform of a sinusoid, then doing all the manipulations, finally reaching up to this point. Are these 2 points clear to everyone present over here? Please write in the chat box. Sharanya, Shabrish, can both of you write in the chat box at least whether the concepts. Okay, Sharanya has written yes, clear, good. Okay, so now it's clear to you. Let me write it for a cosine signal. So once again going back to our old cosine signal, Sn equal to a cosine omega Cn plus phi. Okay, that was our earlier signal. Now what did we tell earlier? We broke it into two complex exponentials, omega Cn plus phi and minus omega Cn plus phi. Okay, so what do you observe? We have one S1 of n and one S2 of n, isn't it? S1 of n, what was that? What was the S1 of n? It is the a by 2 e to the power j phi times e to the power j omega Cn. Omega 1 is omega c. S2 of n, this that a by 2 e to the power minus j phi e to the power minus j omega c n. What is omega 2? It is minus omega c. Now what is the polynomial that I need to form? The polynomial I need to form is e to the power minus j omega 1 z inverse times minus j omega 2 z inverse 1 minus e to the power minus j omega c z inverse times 1 minus e to the power j omega c z inverse. Now let me break them into simpler terms. 1 minus, okay, so this should be plus minus j omega c z inverse minus j omega c z inverse plus e to the power minus j omega c to j omega c z to the power minus 2. Me further group the terms. 1 minus e to the power j omega c plus e to the power minus j omega c z inverse plus these two cancel each other, I guess z to the power minus 2. Now look at this term, what is it? E to the power x plus e to the power minus jx. Okay, so it's 1 minus 2 cos omega c z inverse plus z to the power 2. Okay, look at this once again. P of z is 1 minus 2 cos omega c z inverse plus z to the power minus 2. Fine. Now P of z times s of z was 0, isn't it? So what do we have? S of z minus when you have multiply it with s of z, you get minus 2 cos omega c z inverse s of z plus z to the power minus 2 s of z equal to 0. Okay, now take inverse z transform. Okay, what do I get? I get s of n minus 2 cos omega c s of n minus 1 plus s of n minus 2. Now I can write this as s of n is 2 cos omega c s of n minus 1 minus s of n minus 2, and all of this is in the absence of noise. Okay, so what does this show me? It shows that present sample can be perfectly predicted from past two samples in the absence of noise. Okay, so how do you actually put this into picture? Our objective, what was our main objective? If we go back, our main objective was to find omega c. Okay, how do we do that? Let's say we take this signal s of n. Okay, what we actually do, and I delay this signal and pass it through an FIR filter with coefficients W0 and W1. Okay, let's say the signal is Y and this one is D, and then the error that we get, we put it in the adaptation algorithm or our adaptive algorithm, and what happens over here is that if you look at what is happening, D, let me write the signal as x. D is s of n. What is x? X is a delayed version, so s of n minus 1. What is y? What is y? Y is w0 x of n plus w0 x of n minus 1. And what is xn? Xn is s of n minus 1. W0 s of n minus 1 plus, oops, there should be w1. W1 s of n minus 2. Okay, now what does an adaptive filter do? Adaptive filter minimizes e square of n, which means you automatically en goes close to 0. So what is e of n? E of n is dn minus yn, and from here what can you write? Dn is Sn minus w0 Sn minus 1 minus w1 Sn minus 2. But what did we write earlier here? Sn is what? Sn is 2 cos omega c z Sn minus 1 minus s of n minus 2. In order to ensure that En goes down to 0, where will W0 reach after steady state? W0 will reach 2 cos omega c, and W1 will reach how much? -1. So using adaptive processing, we obtain the frequency omega c from the fast filter tap W0, where W0 is 2 cosine omega c. Fine. So this is an application of this adaptive filter, where we do some frequency estimation. In reality, we have noise. So for a better estimate, we use larger number of filter taps. Okay, so this is our discussion regarding the frequency estimation using adaptive filter. Okay, now now let me talk about certain applications of adaptive filtering. So some notable applications of adaptive filtering are system identification, echo cancellation, channel equalization. Okay, system identification, echo cancellation, then you have noise cancellation. Okay, so all of them you can all of same algorithm but used in a different way. Then you also have interference cancellation. Okay, so now I will talk about system identification. Okay, system identification. So what happens in system identification? Okay, let's suppose you have some kind of a system. What can that system be? That system can be, let's suppose, your room impulse response. Okay, what happens actually in your room impulse response? So let's suppose there is a sound source and you are standing over here. Okay, so at any point of time, if you feel that you're uncomfortable with any concept or any understanding, please let me know. Okay, so what happens over there? The sound can reach us directly but since it is a closed room, there are various paths using which sound can reach us. Okay, multiple reflections can take place. Okay, so here, as you can see, there are multiple reflections. As there are multiple reflections, so if I give an impulse, what will it be its response? So I can say that the impulse response of the room can be okay. So at some point of time, I am able to directly hear the sound. Okay, so this a0 delta n, which means the you give the sound, I am able to hear it instantly. There is no reflection, there is a single at one turn I get that sound. Okay, so that's the direct component. Then after some time some reflections come, sometime some more reflections come. Okay, until a certain extent where the sound is so faint that you can have infinite terms. It's an infinite impulse response in theory, but in practice the lower components are so low, they are so low that you are not able to hear them. They are beyond our hearing limit, below our hearing limit. Okay, so if you plot them, okay, so it's nothing over here. So 0 1 2 3 4 5, after this we don't have anything. A0, A1, A2, A3, A4, A5, okay, all the way if I go down. So this is the h of n. Now let's say for some purpose I want to estimate h of n. So what is a method to do that? That is the system identification. Okay, our objective here is to identify what is a0, what is a1, what is a2, till something that we can tolerate or something that we want up to a certain range of L. Okay, so we first model this entire room as an unknown system. Okay, and this unknown system has a impulse response h of n. For our case, we'll consider it as a finite impulse response of length L. So it will be L minus 1. Fine. So x of n, some signal x of n, which let's say music, some white noise, or anything that you give in the input, and then you get some desired signal, some signal dn, and apart from that you may have some outer disturbances or outer noise. Okay, now comes our algorithm part. Okay, so what do we do? We take an adaptive filter w0, w1, level till w of L minus 1. If I want to this choice of L is upon us. There is no fixed thing that you have to take 2 tabs or 200 tabs. It is application dependent and the intelligent choice of the engineer, as well as you need to have some good idea about what you are trying to model. Okay, so you have this xn over here, you have this FIR filter. Note that here w0 to wl minus 1, all of them are time varying. Okay, they will vary with time. So this signal output is yn, this one, Okay, I'm not writing this as dn. Let me write this as d of n. Okay, so here is a subtractor, so it's dn minus yn. I get a signal en, and what do? I do an adaptive, I use an adaptive algorithm. Okay, so what does this adaptive algorithm do? It tries to manipulate w0, w1 all level wl minus 1. And what do you actually get? Let me show you. So in the previous week I had taught the concept of optimal or Wiener filter. So what will be the optimal case? So let me denote the system. This is the unknown system. Okay, the corresponding FIR response up to L taps is given by H vector. So I write as the system coefficient vector. Okay, and the input signal vector is written as this x vector in xn minus 1 xn minus L plus 1. Okay, first what do we take? We take the cross correlation vector between what? Between xn and dn. How do we write that? This p vector is expectation of xn times dn. Now what is dn? If you look at it carefully, dn is d0 of n plus the noise. Let me write this. This is my noise. Okay, and what is d0 in terms? If you see carefully, it is the unknown system. The unknown system I am modeling it as a FIR filter. So what can we write it as? Simple filter equation. dn is H transpose of xn plus neon of n. Is this point clear? Shabdish and Sharanya? You can write in the chat box. Okay, so okay, so fine. So this d of n and is actually summation of the filter of the actual system output. Okay, for an input I get the output from the system, that with the background noise. That's our dn. So let me write p of n once again as expectation of x of n. This d of n is a scalar. Okay, so for what, let me write this in a corner. For a scalar a can be written as a transpose. Okay, because scalar is a single 1 cross 1 matrix. Okay, so one matrix, its transpose is the matrix itself. Inverse of a 1 cross 1 matrix is 1 by that number itself. Okay, So this is a trick over here. Expectation of x d transpose of n. Okay, now expectation of x n, now you can write this here, h transpose of x n plus nu n transpose. So if I break them, what do I get? This is a transpose b, so this will be x transpose n times h transpose plus its nu of n. It's a scalar, so it will remain as it is. Now let me break the summation and take them outside. X transpose x, x transpose of n, h transpose plus expectation of x bar of n, nu of n. Okay, now h bar of n is a constant, h bar transpose h is a constant because it's a system vector, so it's nothing probabilistic. Oops, I am writing this as n h, x transpose of n names h transpose plus okay, so xn is the input signal, nu n is the noise. The noise, okay, there's some noise coming from outside and I'm speaking. The process of my speaking is independent of the noise that somebody is generating outside. They are not correlated with each other. Okay, so they are independent processes. So as they are independent, I can decompose the multiplication in this way. And okay, so I did not I should have mentioned these. What should I mention? I should mention that nu n is 0 mean and independent of xn. Okay, so since expectation of is a 0 mean noise, I can break this down to 0, and what I obtain, I get 0. And what is this? This is our autocorrelation matrix. This is the column vector, this is the row vector. A column vector multiplied by a row vector is a matrix. N cross 1 actually should be L cross 1. This is 1 cross L. I think I should decrease the width. 1 cross L. So yeah, it's much better now. Of, so it's a matrix. Okay, and this matrix is what we call the autocorrelation matrix, Rxx, and this is, oh, there I did a mistake over here. So this is the transpose, and as I take the transpose, I should remove the transpose gets out. Okay, it will be out. So Rxxh plus this is 0, so it doesn't stay. So P I can write as Rx x times h. Okay, and in our previous lecture we learned that the Wiener filter or the optimal filter W opt is what? The W opt is Rxx inverse of P, right? So Rxx inverse, let me substitute this value, this P over here to Rxx into H. Now this inverse cancels with the other. Let me write that down in case you are following the notes. Rxx H, this is identity matrix, then I get H. So what happens? The ideal filter W opt is equal to your system vector. So what does it mean? Means that the optimal filter coefficients match the actual system response. Okay, and when this happens, what is our error? Our error, which is actually dn minus yn. Okay, and what was dn? Dn was d naught n plus nu of n minus y of n. What was d naught n? D naught n was x transpose h. This was nu. What is y? Y is w optimal. Here we considering w optimal case, we transpose x. And here it's h transpose x. So x transpose h minus h transpose x. So both are the same. So they boil into 0. I get noise. So what is this? Best case scenario output noise equals background noise, and that means there is no mismatch error. So no mismatch error meaning that mod of, or if I take w of n minus h, okay, so it should actually be w minus h is equal to 0. So what have I written over here? Let me write that down clearly. Let's say the vectors, the filter, if I filter has converged, I'll tell what convergence means. As finally you are getting down to this value, your filters, your FIR filter over here has reached some steady state value, okay, and h is h0 h1 till h of l minus 1. So you know these are all vectors, so they are vectors. Norm 2 square, what do we write? We had talked about norm 2 several weeks back. So it's the difference between the coefficients w0 minus h0, w1 minus h1 all the way till wl minus 1 minus hl minus 1. This is also is called the L2 norm or the Euclidean norm. Okay, so that's what we mean by that there is no mismatch error. Okay, and now how do you check the performance? How do you check whether this algorithm is working or not? Okay, so the performance, there are two performance metrics for analyzing performance of an adaptive algorithm. The first one is mean squared error, or a better version is EMSC or excess mean square error. Then the second one is MSD, mean square deviation, and an even better version of this is the NMSD, is the normalized mean square deviation. So I am taking a 5-minute break. You can do anything you want in this break. So it's 9:03 now. Let me write over here 5-minute break. Okay, I'll resume at 9 p.m. Okay, so you can refresh yourselves up. I am switching off the camera for now. Okay, so welcome back. I hope everyone is back. Please respond if you have come back in the comment section. I will resume only after that. Okay, Shabrish has come back. If Sharanya, can you please let me know if you have come back or not? Okay, so both of you are present. Good, thank you. So I think I should keep giving breaks at least so that you can refresh yourselves, and a lot of there's a continuous flow of information from one side, so you can take time, relax, and refresh your mind, and after some time you can get back to things. Okay, so as of now we have been talking about um, system identification, in which suppose you have any kind of a system. It may be your room, it may be some acoustic path. Okay, it can be any kind of system. Okay, there are infinite such applications where system identification is required. For example, in suppose hearing aids, there is a or hearing aids or any other acoustic system, there are feedback paths. Let's say I'm speaking near a loudspeaker with a microphone in hand, then the feedback takes place. Okay, the loudspeaker amplifies the sound that I spoke, and that output is again fed as an input to the microphone, and that amplified noise gets even more amplified, so a positive feedback loop takes place, and then we get a keych kind of sound in the screeching sound in the amplifier because of saturation on the system. So that kind of feedback can also take place in our hearing aids, because the distance between the microphone and the speaker in the microphone, they are very small in size, but because the size is really small, so that feedback inevitably takes place. But unlike the microphone in the stage situation where you can move away. Okay, like let's suppose I switch on my okay, let's do that. Okay, that would be really great fun. So I'm intentionally creating this feedback so that you can get an idea of what is actually happening. Let's experiment that. So I'm going to join this meeting with my mobile phone on. Okay, so see, joined I've
I've
joined this
joined
in
the
session,
session,
so you
so
can
you can
see
see
the
the
feedback
feedback
coming
coming
out.
out.
So
So
as I
as I
move as I move as I move as I move, you see
you see,
this hello, hello. Okay,
okay,
okay, you
okay, you
see,
see,
hello,
hello,
you see
you see
these
these
feedbacks,
feedbacks.
you see these feedbacks now, right? Okay, Sarni and Sabrish were able to get the feedback that was coming out. There were repetitions, there were echoes going on. Yeah, so you're getting this. So yes, you were able to listen to the echoes because I was speaking, then it was repeating, it was catching out. The same kind of phenomenon actually takes place in an earphone as well. Okay, so you keep that voice keeps on accumulating, and then you screech up. Okay, so you get that high kind of a noise. Now because the distance is really low, you can't separate them far apart. Okay, it has to be there in your hearing aid, so you have to invariably kind of eliminate this feedback path, the feedback that's going, and for that you have to generate the same kind of noise that the feedback is generating. Okay, so in order to be able to generate that noise, what do? You identify the system, and when you identify the system, okay, so when you identify the system, you are able to produce the same kind of sound through the adaptive filter, and because of this cancellation over here, you get a noise free, a feedback free sound. Okay, so that's the principle used in a lot of noise cancellation earphones as well. Maybe we will not discuss this here, but then essentially the principle is the same. Let me remove this thing. Good. So what actually happens initially? Okay, so as mentioned, in any of our adapt, oh, it's too thick. In any of our adaptive algorithm, we have something called the cost function that we denote over a j. Now let's for suppose for the LMS or the least mean squares algorithm, what was our j? We learnt in the previous class. The j was actually e square of n. This is the instantaneous error squared. Okay, I'm not taking the expectation, as I mentioned earlier. The expectation, if you take, will actually give you the ideal value, but then here we want to implement it in a with lower complexity. Okay, we don't want to get into multiple samples, taking their average, divide them, and keep on multiplying stuff. Okay, we don't want to, we are taking a wild estimate, so we take the instantaneous error as the cost function. Okay, and so what happens initially? When we start our algorithm, the weights w, they are initialized to 0. So all, say, w0, w1, all of them till wl minus 1 is, all of them are initialized to 0, and from you can initialize it to some other value as well, but from a implementation perspective, we are able to, it's easiest to implement to 0, because these you are storing these w0s in some registers. Okay, we have talked about registers in the first 2-3 weeks. So you can reset a register, and when you reset a register, it's all zeros, so you are storing them as zeros. So w bar is 0 and h bar is as it is. Okay, so what you actually get initially, en is dn minus yn. So dn was x transpose of n times, and let dn be dn, and x transpose of n times w of n. Wn of n, wn is 0, so you get dn. So initially your error is actually high because it depends on dn only. Okay, it's a finite value, so error is high. So if I plot j versus samples, so what happens is that initially your j is high. Okay, and assuming that we had shown last week that we had this j versus e curve, where I guess Fabrice was there in the session, so you must be knowing that we had this optimal value. So initially we were at some this kind of value, and assuming that mu is small enough so that I don't diverge, I first moved down to this, so, and then I moved on to this, and slowly iteration by iteration I move around w opt. Okay, so, and in fact I had drawn this also earlier. So what happens, I go down until there's actually a point I saturate, okay, like this. These points, this point, let me denote this, this, this. There is nothing much to say over here, but then look at this, it has saturated at certain point, and now it saturates to a finite value. And what does this correspond to? This value actually corresponds to, now we are assuming over here that the although it does not look so from the diagram, but we are assuming that over here the W has almost become very close to H. Okay, that means we have all our filter coefficients are reaching the system response values. This bar where it has stopped, this is called the noise floor. Okay, why noise floor? If you look over here earlier, there was some background noise in this case, okay, this nu n, and when we went to the optimal case, okay, the optimal case, what did you obtain? You obtain that when you have completely converged in ideal case, when W optimal is same as the system coefficient, then your error is nothing but the background noise only, nothing else. So best case scenario which you mentioned, output noise equals background noise. So your cost actually converges down to a noise floor. So in MATLAB, what do? We actually plot 10 times log 10 base e square. We do all of them on a logarithmic plot, so that we can, because we note down powers in the dB scale. So this is in dB scale. So what for example, when we say that nu n can be additive white Gaussian noise with signal to noise ratio of say 40 dB. Okay, so what we obtain over here is that your algorithm should settle down to 40 dB. This is I'm showing what happens in the ideal case, but in reality, because we have used this e square of n, okay, this e square of n is here. Now it's not the same as expectation of e square of n, okay, it is e square of n only. Had it been expectation of e square of n, it wouldn't have been better, but because we are simplifying our cost function, we are injecting some kind of an error, and because of some that injection of this error, what you get is something of this sort. Actually, if you really implement this in MATLAB, you will be able to see these kind of plots, okay. So for LMS, you this color I give for the LMS, okay, depending on assuming that you have used a step size which is small enough to converge correctly at the right coefficients, and then the expectation is and then the convergence is in the mean. Why I am saying the mean? Because if you see, it is the error, this is oscillating around the noise floor, okay, it is not stable, becoming stable, it is moving around, okay. This is because this is the noise injected due to this approximation of the cost function. Fine. So and that's when you use an optimal mu. Now what happens when you choose a very large mu, or let's suppose I choose, let's say this was, I chose mu1 over here, and now for the same case of LMS I chose mu2, where mu2 is larger than mu1, but both converge, okay. I'm not saying that the one will diverge. There is another case of diversion, but assuming that they are in some kind of a limit, and let me tell you, it's just for a knowledge, it's not there in this course. If you take some adaptive signal processing full course, then you will be able to see that there is some kind of a bound, that the step size parameter, if you look at LMS, where wn plus 1 is wn plus mu, I shouldn't have written this, en x bar of n, then this mu has to is bounded is lies must lie between 0 and 2 upon trace of the autocorrelation matrix. This xn autocorrelation matrix had been mentioned a lot of times, so now you must have understood this autocorrelation matrix rxx is expectation of xn times x transpose of n. Okay, this is the autocorrelation matrix, and this mu is bounded by this value. So I'm assuming that mu2 and mu1 is within this bound. So what will happen in this case? In this case, since we are going too fast enough, so you see over here, let me draw it first. This is actually what happens. So you tried to move in faster, but then you ended up at a higher noise. And why is this happening? See, if I move from here, large step size, no, I will keep on oscillating between over here. I will never reach here. Why is this happening? This is like your footsteps. If you take small footsteps slowly, you will finally reach at this point because you are moving small enough. Okay, but then if I move too large, okay, like this, and after some point, because convergence has to take place, I will not move up like this, but then what is happening? I actually end up moving around this point. Okay, I never reach this point. I just keep moving left and right around this point, and because of moving left and round around this point, I have some kind of a deviation from this ideal value. So what actually happens in this case is, there is some finite difference between the vector h, the system coefficients, as well as the estimated value from w. So that's why this includes some kind of a what you call this that I mentioned earlier, mismatch error. So there is mismatch between the estimated coefficients and the actual coefficients, because of which you don't converge to the noise floor. Let me write this down over here. This is the noise floor, and what does this mean? Mismatch error due to fast convergence. Okay, this is very similar to what happens when you take decisions in your life in haste. Means you don't give time to things, and you don't analyze things properly and slowly. When you in very less time, you may reach a decision, but that decision may not be optimal. So this is also the case with adaptive signal processing as well. So that's signal processing in real life. I think somebody has typed something. Oh no, it was that message. Okay, so this is what you call the mean square error, or the MSE plots. So another kind of plot that you can have is the EMSE, or the MSE minus the noise floor. Okay, Okay, so what will it happen? It will be the mean square error minus the noise floor. So the lowest value that you can get is 0 in the ideal case, and for the mismatch you get something like this. Okay, so this is the EMSE plot. So let's say it started from something, let's say -20. So here it was 40, so 20, so you move that up by 40, so you get this 20. Okay, excess mean square error minus the noise floor. Okay, so you are kind of removing the dependence on the noise floor. Okay, another one is the mean MSD, or the mean square deviation. So what is mean square deviation? Mean square deviation in log scale, we write it as 10 times log 10 base the vector w of n minus the optimal one in the whole square. So here what you are doing, rather than looking at the signal error E of n, you are looking at how close is your this vector to the actual one. And when you look at the normalized version, what do you write? 10 times log 10 base norm of wn minus h bar whole square by norm of, I should add 2 over here, h bar whole square. Okay, this these MSD and NMSD are not all are used in a special, are not always used, they are used in some special scenarios, in special measurement of measuring the performance of robust adaptive algorithm. Now let me briefly define, I am just giving a brief overview of what happens in robust adaptive algorithm, and then I will well let me know is if there is anything else to be covered from this week's class. Please mention that, because I have mostly covered everything in previous week and this week as well. Saranya and Shabrish, any further thing to be covered from this week's lecture? Because this is something extra that will be that I will be covering from my end, but it's not there in the course. This is just to give you motivation behind in the field of signal processing, adaptive signal processing. Saranya, Sherish, can you please write down if you have any doubts, yes, no, from this session on the adaptive portion. Are you there? Okay, so there are no doubts. Okay, clear. So I am asking that anything else to be covered from adaptive signal processing portion of the okay, so all are clear. Okay, so yeah, we have completed, we actually covered up a good deal of this, almost the entire thing. So just mentioning as a side note, so robust adaptive algorithm, if we look at that, what are they? So our normal LMS algorithm, if we see, is wn plus 1 is wn plus mu xn e of n. I can also view it as a weight increment. Previous and the next weight is the sum of previous weight and some increment. If you look at this increment term, W of n is proportional to error. Okay, now if I plot that, how assignment 8 reference book are there for adaptive filter. Adaptive filter, you can find online several books, but I don't think the books are too advanced for this assignment. So I will write books for the adaptive signal processing portion, but I don't think they will be much helpful for these assignments, because these assignments are comparatively more theoretical, but you may read the first and second chapters. So you can refer to books like Simon Hacking Adaptive. I'm not able to exactly recall the books, but you can type in Google and then find, you'll be able to find them. Just write Simon Hacking and adaptive filters, adaptive filtering, something like, because Simon Hacking has written a lot of books on other topics as well, like signal processing as well as neural networks as well. So especially for Simon Hacking, just type this adaptive filter, so you get the right book. Okay, and then you have Ali H. Syed. Just write adaptive filter celebrity processing book PDF. Then you have, let me check once, R. Diniz. Paulo S.R. Diniz. Simon Hacking additive filter theory, Paulo S.R. Diniz, Ali H. Said, Ali H. Said, adaptive filter. Yeah, so we have another book called, all of them are adaptive filters name, and Berhuz Furan. There's another. Okay, so these three books will be more, I mean, more than enough for this assignment. I mean, this assignment 8 is, no, I said not much, not too mathematical enough for these three books, but you can refer to the first 2-3 chapters of these books. Welcome. So so if you look at the increment, actually I should be plotting a single element, because W bar is a vector, so I should be plotting it with respect to a single weight element. So what will be it like? All values of E, it is linearly proportional. So what actually happens is that normally our En is having some kind of En is having some kind of a distribution, and they are generally Gaussian in nature. So when you have a Gaussian kind of a distribution, then the probability that you have very high values is almost negligible. You have something around 3 sigma, right? Those stuff, 99% between -3 sigma to +3 sigma. Okay, and for real life, this this En actually takes small values, and that does not disrupt the weight update. Okay, but in some scenarios, because of the like horns, gunshots, or maybe lightning, thunderbolt, very high noise, impulsive, which we call as impulsive or heavy tailed actually it should be V of n has this kind of a distribution. Okay, V of n, not E of n. E of n is V of n plus the other stuff. Heavy tailed distribution, so you also call as the stable alpha stable distribution, like Laplacian binary, this S alpha is okay. So these kind of distributions, so they have a good chance of acquiring high values. The error can take very high value, like I'm talking to suddenly some thunderbolt comes, okay, and that is an impulse or heavy tailed noise. So what happens in that case, the when En goes high, Wn also, delta Wn also goes very high, because they are proportional to each other. And because of the proportionality, what happens, if I look at a situation J of n, sorry, where I have converged, and suddenly at this point, okay, at this time index that I am showing over here, I have converged, my system no longer needs to update because I have reached this steady state, okay. But all of a sudden an impulse comes, an impulsive noise comes, and because of that, because En is very high, my delta W will become very high suddenly, and from here I will again get a shot over here, right. I am not supposed to diverge because I have gone steady state, but because there is a lightning behind me, suddenly it goes up, and again I take time to divert. So in this sort, I am suffering from a very big problem. I might lose some information that I was supposed to get during this time, right. So we say that this is not robust to outliers. So what are you supposed to do in such cases, or what should the algorithm do? So in such cases, when En goes very high, delta Wn should be going down or 0. So how will they look like? This delta Wn, so for small values of En, they should behave like LMS, okay, linearly proportional, otherwise our adaptation won't happen. But then when I go to very large value, either you go like this, or you behave like this. So these sort of algorithms where delta W has some kind of see this kind of behavior, these are called robust adaptive algorithms, okay. And in such scenarios, what happens, if you look at the convergence plots, you have converged, and even at this point if I give a shot, it does not change, no issues, I just stay as it is wherever I am, okay. So that's all about robust adaptive algorithm. And when we actually measure the robust adaptive algorithm, we actually, I shouldn't have plotted J, because E actually goes high, so actually what we plot over here is mean square deviation, MSD, or rather I can put a bracket NMSD, okay. So that's it about robust adaptive algorithm. And is this robust adaptive algorithm clear to all? It's not a part of a syllabus, but this is a part of, means people are currently doing a lot of research on this, okay. So maybe in case any of you are doing PhD or want to do PhD, then in adaptive signal processing, then this can be was a good field to look into. There are lots and lots of robust adaptive algorithms that have been worked upon. People still doing work in it, okay. So that's it for today's session. I'm not delaying things further because I have covered almost everything. So thank you and good night everyone.